Hello everyone. So in chapter 3, we're going to be investigating what's called independence. So for this chapter, what our focus is going to be is understanding what it means for attempts to be independent, determining when evidence in a hypothesis test is statistically significant. That's again relating back to the idea of p-values, comparing that to the significance level. And then we are going to compare and contrast type 1 and type 2 errors. Briefly, what those are is there when we're comparing the p-value to the significance level. So let's say that the p-value was 0.02, and then the significance level was, we're just going to stick with 0.05 or 5%. Let's say that we got data that gave us this p-value, but in reality, the data should have given us something else. So let's say we were to have, using the law of large numbers, we would have been able to get a more accurate number of this. And let's say if we did that, it gave us 0.08. So the idea of the errors are basically when the p-value tells us one thing, but in reality, it should have been another thing. Okay, so some terminology. An athlete's attempts are independent if his or her ability to be successful is the same after a successful performance and after an unsuccessful performance. So in other words, their future performances will not be affected by their previous performances. So one example is Kyle. He's a basketball player, and his shot attempts are independent if the success of one shot does not depend on the success of a previous shot. One example of this is, let's say Kyle was given 2 free throws, and his first free throw was a miss. It would be independent if that miss didn't affect his second free throw, meaning that the idea of him missing or failing on the first one didn't mess up his mindset and make him think he was going to fail on the second one and therefore affect his performance that way. Another example would be Michelle attempts at flipping a coin and is wanting it to land on heads. Those are independent if the success of one flip landing on heads does not depend on the success of a previous flip. So obviously, if you're flipping a coin, every single one of those is going to be independent because the coin doesn't matter if it just landed on heads or it just landed on tails. So another terminology is hot hand. A player has what's known as a hot hand if his or her ability to be successful is higher following a success rather than following a failure. So going back to that free throw example, which we will investigate further in this chapter, but if the player makes the first free throw, then they would have a hot hand if that would mean that their success for the second free throw was greater. So in other words, when a player has the hot hand, the percentage of success following a success will be higher than the percentage of successes following a failure. So for this one, it is testing the hot hand streakiness. This is the title of this section. The scenario for this is on September 7, 2008, quarterback Tony of the Dallas Cowboys had a streak of 9 consecutive completed passes, suggesting that he had the hot hand. The following sequences use C to represent a completed pass and I to represent incomplete or an intercepted pass. And overall, Romo completed 24 of his 32 passes in this game. If I'm saying his name wrong, someone please correct me in class. So for each of these, the C's represent completed passes. So C's represent completed passes, and the I's represent incomplete or intercepted passes. So the longest streak in this series is 9 completed passes. So here's that exact same series again. So the driving question is, Does this streak of 9 successful performances give convincing evidence that Rameau had the hot hand? What do you think the null hypothesis is for this question? And what do you think the alternate hypothesis is for this question? Pause the video here and write what you think these are in your notes. So what they are is the null hypothesis is that the outcomes of Tony Rameau's past attempts are independent, meaning that they do not depend on each other. And the alternate is that Tony Rameau had the hot hand. Another way that could have been written is that his previous successes made him more likely to have a success for his next pass. So saying that this success improved the chance for this success, and this success, so on and so forth. And then when he had an incomplete or a intercepted one, it broke that that streakiness that he was having. So next, repeating those, and recall the null hypothesis assumes that nothing changes. Nothing changes. And then the alternate hypothesis is what we are investigating. So in this scenario, it is if he has the hot hand, or in other words, his ability increases following a success. Remember, alternate hypothesis is always something is changing, either increasing or decreasing, and we want to always keep it in the increasing terms. We don't want to state it as decreasing, because then that gives us some confusing p-values. So, Mr. or Mrs. Observant Student, but Mr. Barnhart, how are we going to say if we have convincing evidence? Are we about to learn another way to use dot plots? The answer is yep. So to generate the dot plots that are used to investigate streakiness, we will have each dot represent the longest streak in the simulated game. You remember, or a little explanation, is a streak can either be a good streak or a bad streak. So he could have had a streak of a whole bunch of intercepted, or he could have, like he did, have a streak of completed. Now for this one, there are, let's add one more over here. There are 1, 2, 3, 4, 5, 6, 7 incompletes, and 1, 2, 3, 4, 5, 6 completed. So because the 7 is the longest streak, that's what you would count. So in other words, we are going to assume that the null hypothesis, being that his past attempts are independent, and see what could happen purely by random chance. What this means is that we would take all of his attempts and we would write a card for each of these, shuffle them up, and just see what happens purely by random chance. Okay, so we have the same sequence as before. So here's how we're going to set up the simulation. First, we're going to count the total number of attempts. There are 32 of these. Next, we are going to count the number of completed passes. So we already know there's 9 here, 10, 11, 12, There's 24 of them. And then we're going to count the number of incompleted or intercepted passes. 1, 2, 3, There's 8 of them. So we're going to grab 32 blank cards. We're going to write C on 24 of them and I on 8 of them. Shuffle them and then lay them face up one at a time and record the order. So after we write all these, shuffle them, and then lay them out one at a time, we will get something that looks like this, or at least this is one example of it. After we do that, we count the longest streak. So this is a streak of 5. This is a streak of 7. Streak of 5. And 3. And this one would be a streak of 2, but that's not very convincing of a streak. So we count the one that has the most. So then I made this handy dandy spreadsheet. When it finally loads. And so what this is doing is it's doing that exact same thing where we had, it was 24 and 8. Yeah, so we had 24 completes and 8 incompletes. So there's 24 completions, those are what the ups are, and then there's 8 downs. So this would be one simulation, and the longest streak in this one would be 8. In this one it would be 10. It's over here. Over here it would be 9, 12, 7, 8, 10, so on and so forth. So what we're doing with this is we are just using random chance of the exact same completes and incompletes to see what orders they would lie in. And then each of these numbers is the number that would be recorded on the dot plot. So obviously we don't want to, do this 100 times and then record the number 100 times. So what we do is we have a handy dandy tool for that. And I forgot to animate that part. We'll get into that tool a little bit later, but after doing this process of simulating and recording 100 times, we will get something like this. So this would be a single simulation where there were a streak of 4. These all had a streak of 6. These all had a highest streak of 8, 10, highest streak of 14, highest streak of 16. And so recall that in the observed game, Tony Romo's longest streak was 9. So the question is, was that a convincing evidence that he had a hot hand in that game? So to compare it to this one, everything in this dotted area is games where he had a streak of 9 or more. So just from looking at this, do you think that we would have convincing evidence that he did, or would we not have convincing evidence? Think about that for a second. So to investigate this, Mr. or Mrs. Student says, "Hey, that is neat, but are we about to have to calculate a p-value?" Yep, but it is the exact same process as before. So first we're going to find the observation on the dot plot, and that was 9 for this one. We're going to count the number of dots at or above the observation. We are then going to do the same calculation as before, the counted number of dots divided by the total number of simulations. And going on this one, we would count 1, 2, 3, 4, 5, 6, 7, 8. I'm already feeling like I'm falling asleep. So, Oh, okay. It says take a minute and interpret the p-value if the observation was 9 completions. And if you recall from the previous slide, there are 45 dots in this rectangle here. Okay. So, board student again says, yeah, we know how to calculate and interpret a p-value. You have been explaining and re-explaining that over and over and over. And if you needed me to go over that other one, since there were 45 dots that were at or above 9 completions in a row, we would divide that by the total number of dots, and it would be 45%. So nothing new. So I've been explaining and re-explaining it. So then the next thing is, but what you haven't explained is, why do we say fail to reject the null hypothesis instead of just saying accept the null hypothesis? My response, because I hadn't gotten to that yet. And now we will. So the question, if we fail to reject the null hypothesis, does that mean we accept the null hypothesis? Nope. For the example with Tony Romo, all we can say is that we do not have convincing evidence that Tony Romo had the hot hand. However, this does not mean that we have convincing evidence that his attempts were independent, meaning we do not have convincing evidence that we accept the null hypothesis. What we do have evidence for is that it is plausible that his attempts were independent. We haven't proved it, but we have evidence to say that it's plausible. Keep in mind that it is also plausible that he had the hot hand, but his ability increase was so small we couldn't detect it with that study. So what about cold streaks? So we know about a hot hand streak, but what about a cold streak? What does that mean? So it may seem counterintuitive, but a long string of failures can also be evidence of a greater ability following a success. What that means is if we have this pattern, so win, lose, win, win, lose, lose, lose. So we have a streak here of 6 losses. We can look at it like this. The team was doing decent until they had a streak of 6 losses. So they were doing decent. They had a win, a loss, a win, and win. Then they did really bad in a row. However, after getting a win, this one right here, their ability seemed to return to normal. So another way to say that is they were kind of doing their normal win, lose, win, win, really bad performances. But when they got this win, it went back to what could be considered typical with this. So typical, really bad ability. They got a win, and then their ability increased back to what we could call kind of their baseline. So in other words, the win broke their losing streak, and it appeared to increase their ability. So they were doing this, they got a loss, their ability decreased for this streak, they get a win, and their ability increased back to what it was before. So now we have an example of a streaky team. Seems kind of weird. Anyways, in the 2008 regular season, the Green Bay Packers had 6 wins and 10 losses. Depending on if you like them or not, you might have wanted them to have more losses or more wins. Up to you. So those were highlighted by a streak of 5 consecutive losses. In the second half of the season, does this streak of 5 losses in a row provide convincing evidence, this streak here, provide convincing evidence that the Packers were a streaky team? Or is it plausible that the outcomes of their games were independent and the streak happened purely by random chance? So the results here are in chronological order. So they had a win, win, loss, 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 win, win, loss, loss. You get it. So the first problem in this example is explain what it means to say that outcome of the Packers games are independent. And recall, a team's attempts are independent if their ability to be successful is the same after a successful performance and after an unsuccessful performance. So whether they win or lose, they don't care about that when they're moving into their next game. So pause and attempt to answer this one on your own for a minute. Okay, so the solution is if the outcome of the Packers games are independent, then the outcomes of the previous games do not affect their ability. The previous games do not affect their ability of the Packers to win future games. So next part, state the hypotheses we are interested in testing. So take a minute and write out what you believe the null and the alternate hypotheses are. So the null hypothesis is that the outcome of the Packers games were independent. And the alternate is that the Packers were a streaky team. Another way you could say that is that the Packers' previous performances affected their future performances. That's just what streaky means. So continuing the example, this is the same sequence as before. The problem for this one is describe how to simulate the distribution of the test statistic, meaning the longest streak is what our test statistic is in this case, assuming that the outcome of the Packers games were independent. Work on this one for a minute. So the the means that we would use to simulate this one was first we would collect 16 cards, one per game. So if you were to count these 1, 2, 3, 4, 5, blah, 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 16. Next, we will label 6 with a W because 1, 2, 3, 4, 5, 6 were wins. And then we will label 10 with an L. I know you know how to count. I'm not going to count those for you. We will then shuffle them and lay them out in order. And after we do that, we count the longest streak. And remember, streaks can be a line of wins or a line of losses. So after we do that 100 times, we would put every single one of those on a dot plot. So remember, these are simulations where the longest streak was 2. These are simulations where the longest streak was 3. Longest streak was 4, 5, 6, 7, 8. So the problem is to estimate and interpret the p-value and recall that the observed streak was 5. And while you're doing this, also use the significance level of 0.05. So take a minute, calculate that. So the first thing that you're going to do when you solve this one is you're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah. There are 41 dots that are either at or above 5. And the reason why we're using 5 is because the observed streak was 5. And then since there are 100 simulations, we do 41 divided by 100, and we get 41%. So this is the p-value. Now comparing that to the significance value, remember that 0.05 is the same thing as 5%. Comparing 41 to 5%, this is way over 5%. So we can say that we do not have significant evidence that that they were a streaky team. So Another way to say that, since the p-value is quite large, we fail to reject the null hypothesis that the Packers' outcomes were independent. We do not have convincing evidence to support the alternate hypothesis that the Packers were a streaky team. It is plausible that their streak of 5 losses in a row was simply due to random chance. So remember, just because the p-value that we calculated was 41%, even though that's a pretty big percent, it doesn't mean that we have convincing evidence that the null hypothesis is true. We can only say that it is plausible that the null hypothesis is true. And that's it. No.